right? So as I said, there are many theories to use with two-way slabs. In the IS456, what I showed, they had listed a few of them. One was known as Piget's theory, Piget's curves. Then there is Westergaard theory. There is this Rankin-Grashof theory, which I just mentioned in the PPT. And then there is this thing known as RealLine theory. So among all these theories, the two of them are more commonly used. One is the Pigeard's curves. Pigard in the spelling is Pigeaud. Pigard, it's a French name. So Pigeard's curves is it's a graphical theory where they have many charts relating, the stiffness of the slab with moments along different directions. Okay, probably tomorrow, if possible, I'll try to show you one. Or even today itself, if at the end of the class, if possible, I'll show you. So that is one thing, but it's more commonly used for bridge decks. Okay, to design the deck in bridges. So that is where Piget series is more commonly used. That too used these days. Hardly anybody uses it because people have modeling software where they just model the deck, apply the load, and get the results. But analytically, if somebody wants to do it, a few decades ago, Piget's curves was very useful to actually design bridge decks. So that is one theory, common one. And the other one, which gives you a more physical representation on how a two-way slab will fail and what the failure moment of a two-way slab is. So in order to find this, RealLine theory is the most common one which is used. Now, as the name says, it basically depends on the yielding of the particular slab, yielding of the reinforcement in the slab, rather. Okay, so that is what this theory is actually based on. Another thing that you should notice is the moment coefficients which we saw in IS456, those are more applicable to, they have some limitations. One of the limitations is it is more easy to use them for design rather than using them for analysis. Okay, so there's a difference between design and analysis. I hope you know them because you're halfway through this course. So, I mean, does anyone know what the difference basically is between analysis and design? If I give you a beam, uh, so how do you differentiate between whether you have to do an analysis or whether you have to do a design? Okay, don't say that in the question. It'll be mentioned design and or it'll be mentioned analyze. Not that's not what I'm asking. No. What is the difference between analysis and design?
So if the dimensions are given and I have to find the maximum resisting moment, then it will be
Yeah.
analysis. And
Okay.
if you are given the moment and then you have to find the dimensions, then it's design.
If you want to find the dimensions and the reinforcement, that is known as design. Okay, so exactly correct. So basically, you're given something, okay, and you want to know under what circumstances this is useful, or on what circumstances this is going to function well. That is known as analysis. If you're given a particular function and you want to find a component or make a component to satisfy that particular function, that is known as a design. So the moment coefficients are more directly applicable to do design of slabs. Okay, basically because you know the load, you know the thickness of the slab, LY by Lx, everything is known, and you want to just find out how much thickness you should give and how much reinforcement you should give, positive and negative. So the moment coefficients are actually more useful for that. Another limitation of that particular thing is uh, the slab itself. It should have only very standard cases like all four edges. I mean, it should be a rectangular slab. It should not be any random shape. It should not be trapezium. It should not be triangular. It should not be circular. It should be only rectangular slabs. Okay, and the other thing that is to be mentioned along with it is it should have fully uniformly distributed load. You cannot have point loads. You cannot have partial loads. You cannot have anything else. Okay, and the boundaries also, it should be perfectly on the outer edges of the slab. You cannot have a slab where there's the supports are inside and there's a little bit of overhang. See, for example, you know your overhanging beam. Okay, you just imagine overhanging in terms of a slab. Okay, so you cannot have you cannot have a rectangle forming the boundary of the supports, and you cannot have your slab which is bigger than that rectangle and having some overhang on all sides. So you cannot have that kind of a slab as well. So there are many practical slabs which do not fall under those categories, and in such cases you cannot actually use those moment coefficients, and you need some other way. So there are several shortcuts to do, but one of the most technically very meaningful ones is RealLine theory. So what is this RealLine theory? Okay, so basically RealLine theory means it is something which says when does the reinforcement yield along x direction and when does it yield along y direction, and then based on that it tells you what the based on that you will be able to, using some analysis and calculations, you will be able to predict to attain that state where both the directions reinforcement has yielded, how much moment is required or how much load is required. So that will be the capacity of your slab. So the principle is based on something known as redistribution of moments in continuous beams and frames. It could also be slabs. So the analysis of slabs spanning in two directions at right angles, you can use RealLine theory or any other acceptable method. Alternative provisions in Annex D may be used. So this RealLine theory, why they specifically mentioned RealLine theory is it's because it's the most common. So you have a slab, rectangular slab over here, supported on our four sides. Let's assume that this is two-way, Ly by Lx is less than 2. Let's assume that's the case. And you have a very random boundary. This is discontinuous, this is continuous, these two are continuous. Could be anything. Okay, it doesn't matter. RealLine theory works for all boundary conditions. It works for all shapes as well. And let's say that depending on our actually this is an image taken from somewhere else, so it's basically the same thing, alpha x w lx square. Okay, f is nothing but l into x, so it's basically giving you the same thing, same information, and say that you're finding x span moment, y span moment, and similarly support moment here, support moment here, support moment on the top, and support moment on the bottom. So you know all of these moments along x and y direction. Okay, so whenever you have a two-way slab, in general, the bending moment along x direction and y direction will not be the same. Okay, and in the direction of the larger bending moment, the reinforcements will yield before the reinforcement yields in the direction of the smaller bending moment. Now, here I want to ask something that I've already stated. Which direction has the larger bending moment and which direction has the smaller bending moment?
Larger bending.
Larger bending moment will be on which direction?
Shorter span.
Along the shorter span. Yeah, on the
Yes.
shorter edge. Exactly. Okay, I mean along the shorter span rather. And the larger bending moment will be along the smaller bending moment will be along the longer span. Okay. So in general, what will happen is whichever direction, this is rectangular, so I'm able to say shorter span, longer span, larger bending moment and shorter bending moment. Okay, but sometimes it will not be the case. So as shown over here, so you'll have reinforcement along this direction. Okay, going like this. You will also have reinforcement along this direction. Okay. So what happens is, I think I'm showing this for a. Okay, fine. So you have a case like this. And since I told you the bending moment along this direction is larger, the reinforcements which are oriented in this direction will yield first. Okay, this direction, the reinforcements will yield first. Okay, now this does not mean that the slab will collapse, because you have two directions, you have reinforcement. It's a slab, it's not a beam. Okay, if a beam reinforcement has yielded, then soon there may be collapse. Okay, if you don't take corrective measures. But in this case, for a slab, especially a two-way slab, of course, you do not want it to yield. That's not a good thing to have. But even in the case that it yields, it's not going to collapse immediately. Okay, so what rather happens is, once this side has yielded, all the directions are on the, which is oriented along the y direction, if all those reinforcements have yielded, then if you increase the moment further, if you increase the bending moment further, the slab cannot take any bending moment along this direction because already the reinforcement has yielded. So it is not possible for you to have a greater bending moment along this direction, even if you increase the load. Okay, so because of that, what happens is this direction reinforcements have yielded. Therefore, the bending moment cannot increase along this direction. So if you increase the load any further, what will happen is load will stop going to these edges. Rather, the load will start going to these edges now. I mean, always load will go to all the edges, but from this point on, the majority of the load will start going to along the longer direction because it has yielded. Because along the shorter direction, the reinforcement has yielded. So therefore, moment cannot increase along that direction. So the loads carry to the other edges. As long as, of course, this should not be a simply supported edge. If it's a simply supported edge, it cannot take any moment and you cannot have any redistribution. Okay. So if as long as the edge is continuous, the load will be redistributed to that particular edge after this side has yielded. So basically, it's a very simple principle. You have two directions. One direction has yielded, so therefore the moment cannot be taken along that direction anymore. So any increase in load has to go to the other direction where it can be transferred. So it just now starts getting all the load starts getting transferred to the other along the other perpendicular direction. So as long as it's not yielded, depending on the normal aspect ratio and all those things, there will be a certain ratio in which moment goes to the long edge and what ratio it goes to the short edge. So that will be the general case. But once the yielding has happened, shorter direction cannot take any more moment, and therefore it starts going to the longer direction. Okay. So this process will start, and at one particular point, after you increase the load to one particular stage, what will happen is this direction will also yield. Okay. Okay. At one particular stage, now since all the loads have started going to the longer direction, as you keep increasing the load, at one fine point, even the reinforcement along this direction would have yielded. Okay, and now along y direction also all the reinforcement has yielded. Along x direction also all the reinforcement has yielded. And if all the reinforcement has yielded, you cannot increase the moment any further at all. Okay, and this is called as the collapse load of your slab. So this process, okay, whereby the loads can be transferred to the other two edges, thereby increasing the moment in that particular direction. So this is known as a redistribution of moments because basically that is what is happening. Moment instead of going to all the direction, it is now started getting redistributed entirely to one particular direction. So that's why it's known as redistribution of moments. Very simple process. And this RealLine theory, the conveniences, it can be applied to any particular type of slab, any particular type of support, and any shape as well. Okay, so it's useful for rectangular slabs of unusual edge conditions. Okay, for example, a free edge. Okay, the table which you have in Annex D, it has continuous edge and discontinuous edge. Discontinuous means it still has to be supported. It has to be a simple support which is not capable of taking moments, but it should not be free. Okay, it should not be a free edge. But if you use the RealLine theory, you can just about take any particular type of support. So if you look at this and this are clamped or fixed, meaning it can take moment. This edge and this edge are free. And at the vertex of these two edges, you have a column directly supporting the slab. So this is an unusual edge condition. This can also be analyzed by RealLine theory. Different shapes, such as quadrant of a circle or a circle itself. Okay. One good advantage of it is you can actually design with a good bit of economy, because what you're doing here is you're not saying that once the first direction reinforcement has yielded, you do not say that the slab has collapsed. You make use of this concept known as a redistribution of moments, meaning that even after the particular direction reinforcement is yielded, it will get redistributed to the other direction. So you have some gap between the first direction reinforcement yielding and the perpendicular direction reinforcement yielding. So there's a good amount of gap in load which the slab can take between the yielding of the between the first yielding of the reinforcement to the yielding of the reinforcement in all the directions. So you have some amount of load which can be taken within that gap. So therefore, you have a good bit of economy that you can utilize. Since the inelastic capacity, why I say inelastic capacity is because we are going until everything is yielding. All the reinforcements are yielding. So you're making use of the inelastic capacity up to the formation of the yield line. However, when you use the moment coefficients, what you've done previously, so for example, so let me just go back to that. So if you look at this, this is what your moment coefficients are based on. So you have here D. D I told you is analogical to EI. E is Young's modulus. Therefore, this is applicable only in elastic. Okay. All these moment coefficients which you have derived, they are under the assumption of material is elastic. Okay. So you do not talk about yielding at all in this. However, here you go past yielding. So therefore, you have greater economy. You can also use it for non-uniform loadings like a point load. If you have a point load anywhere, you can also use that. Okay, so some definitions. Yield line. So the yield line is a line across which all the reinforcements have yielded. Okay, it is a line across which all the reinforcements have yielded. Yield line pattern. So for example, if you have a particular slab, first one yield line forms, then there's some redistribution, then another yield line forms. So there are situations where you can have more than two yield lines. So you may have several yield lines. All these yield lines will have to form before the slab can collapse. So a yield line pattern is whenever in a slab there are more than one yield line. So the pattern of all these yield lines together formed prior to collapse, that is known as a yield line pattern. Collapse mechanism. Okay, so there's an order. First, the reinforcement along these directions may yield. Then there will be some redistribution, and then some other reinforcements may yield. And when you have slabs of unusual shapes or unusual support conditions, you may have even some more yield lines or some more directional reinforcements which may have to yield. So this order by which first this yields, then that yields, and so on. So this is known as a mechanism, and finally it collapses. So therefore, it's known as a collapse mechanism. And the collapse load is the final load at which the last yield line forms and the collapse is going to happen. That corresponding load is known as collapse load. So these are things that I can ask in theory. Like, what are the advantages of yield line theory? What does a collapse mechanism mean? Give an example for it in your own, using your own imagination, things like that. Okay. So for example, let me take a look at this. This I'm showing a one-way slab, which is supported on AA and BB. So there's a support here and there's a support here. I told you it's a one-way slab supported only on two edges. So therefore, your main reinforcement is going to be only along this direction. Let me say that I give it like this. So I've shown at one location. Like this, it will be there throughout the width of the slab. These reinforcements will be there. This is a one-way slab. You have only one main reinforcement. You do not have reinforcements. You have reinforcements, but they are not main reinforcements. They are just distribution bars. In the opposite direction, you will have only distribution bars. You will not have main reinforcement in the opposite direction, in the perpendicular direction rather, for a one-way slab. So in this case, since this is a one-way slab, once the reinforcements on this, parallel to this AB, so once these reinforcements yield, you will not have any redistribution because there's no other direction on which you have given any main reinforcement. You have given main reinforcement only along one particular direction, which is this, okay, AB. So therefore, there's only one yield line which can form, which is the line connecting all these reinforcements. So this is your yield line. So I told you this is one reinforcement like this. Some other spacing, another reinforcement you'll have another reinforcement here. Similarly at the bottom as well. And when they yield, so the approximately the moment is going to be maximum at the middle. So it is going to yield at the middle. Okay, because that's where the moment is maximum. WL square by 8 midspan, the moment is maximum. So therefore, all the reinforcements are going to yield at the middle. So this line connecting the points at which each of these reinforcements have yielded, that is known as the yield line. Okay, so I have just shown one reinforcement like that. You have several reinforcements parallel to this. Okay, so this is what a yield line means. It basically connects the point of yielding of all the reinforcements. Okay, so if I view this in cross section, this is how it will look. You have UDL. Okay, and so these are only two simply supported edges. Other edges are free, so therefore that's it. You do not have any other support where the moment can redistribute. Okay, you do not have any other direction where the moment can redistribute. So therefore, the first yield line itself will cause collapse. Okay, and what happens is this is an interesting thing about about mechanisms. Okay, so in general, if I have a slab and I look at this, in cross section. This load is applied. What will be the deflected shape of the slab along this direction when I view it along AB? What will be the deflected shape? What kind of a shape will it be in general?
Parabolic.
It will be parabolic, or it will be curved. Okay, it will be a smooth curve. That is true only as long as the mechanism has not formed. If a mechanism forms, we assume, or we kind of, it's not an assumption, it's quite valid. What will actually happen is, if if there's an yield line which has been formed, okay, then that particular between that particular segment where the yield line has formed, you will no longer have a smooth curved deflected shape. Okay, it will become like this. Okay, the parts of the slab on the two sides of the yield line, they act as rigid parts, okay, rather than as flexible parts. Okay, meaning that it's going to be composed of straight discontinuous lines rather than a curve. Okay, the reason why this happens is you no longer have any moment, you no longer have any additional moment carrying across from this point to this point. Okay, there can be no additional moment that can be carried across the point C. Okay, that's why you particularly use the word very carefully, additional moment. So whatever moment was required to cause the yield line, that moment will be there. Further additional moments cannot be carried across. Okay, so in other words, these two segments start behaving like elastic segments. Okay, so this is one major difference in behavior, and this is known as a mechanism or a collapse mechanism. So how to identify a collapse mechanism? If you have any structure and you do an analysis and you see that the deflected shape is all composed of straight lines, even though you have bending moments. The deflected shape is all straight lines means then you know that you can identify that is a mechanism. If it is not a mechanism, if it is not going to collapse, if it's not a collapse mechanism, at least you will find some part of the structure where the deformation is, smooth, like flexible parts. It will not be looking like this with rigid parts. So these are some key differences. The reason that I'm telling you all this is this actually tells you visually some aspects with regard to collapse of a slab. Okay, so you can assume that you just imagine that you have a concrete beam. Okay, it's bending through a nice parabolic, or you imagine even a steel beam. Doesn't matter whether it's concrete or steel, whatever it is. So if you take it and you give it a load, central point load or whatever it is going to bend nicely as a parabola. But at the point where it's going to fail or it's going to break, okay, at that point, if you observe it, you will no longer have a perfect parabola. It is actually, when it breaks, it's going to break as two straight parts. It's not going to break. When it breaks, it will not still remain as a curve. Anything which is going to break, any beam, after it breaks, it's not going to be curved. It's going to become straight. So it's more or less represents that. Let's look at some more few cases. This is also a one-way slab, except that it's not simply supported, rather it is clamped. Okay. Now the major difference between the previous simply supported one-way slab and this is, in a simply supported slab, you have bending moment, maximum bending moment only at the middle, and there's nothing at the supports. However, when you have a fixed two edges fixed slab, like this, you have a nice positive bending moment at the middle, you have a nice negative bending moment at the supports. Okay, and therefore in general for a normal fixed slab, these are your bending moment values. So you have done analysis of indeterminate structures. Okay, so what is the fixing in moment for uniformly distributed load? Fixing in moments for uniformly distributed load, do you remember?
So minus W square by 20
20 fixing in moment.
or 24 sir, by 24.
Oh, no, it's actually 12. I just go back to it. It will be plus or minus WL square by 12. So for the left edge you take minus, and for the right edge you take plus. Okay, so it's actually by 12, not 24. 24 is the midspan moment for a fixed in moment, a fixed beam. The same thing can be applied to this slab. So therefore you have bending moments. This WL square by 12 is more. WL square by 24 is a smaller value. Okay, now by looking at this picture, I can say that I will have 3 yield lines. Okay, one is for the positive moment corresponding to this moment, and I'll have 2 more yield lines which correspond to the, because I have a moment at the support corresponding to that moment, I will have 2 more yield lines. I call them as the negative yield lines because these are negative moments. Now, among positive yield line and negative yield line, which yield line do you think will form first?
Positive.
Positive. How?
Because the value is less, W square by 24.
Okay, the moment is less. So why should it form first? When will a yield line form? If the moment is more or if the moment is less? When will yielding happen? More moment or less moment?
Yes, ma'am.
Yielding is a type of it's a type of failure. So failure will be caused by high moments or low moments. Come on, continue to answer. It's okay.
High moments.
It's going to happen at high. Only higher moment will cause yielding or any type of failure. Let it be. So now coming back to this, which yield line will form first, positive or negative? Compare this and this figure. Which is high, WL square by 12 or WL square by 24?
W square by 12.
12. So which will form first?
W square by 12.
Negative yield line is going to form first. Okay. So at that particular point, when for this one-way slabs, maximum moments are at the fixed edges, and hence the first yield lines will form there, or the negative yield lines will form first. So what happens is, after this negative yield lines are formed, this particular beam will start behaving like a simply supported beam, because this support will no longer take any additional moments. Okay, and any support which does not take moment, we know it's a simple support. Okay, so beyond this point where the negative yield line forms, there will be no further increase in moment at the supports, or henceforth the beam behaves like a simply supported beam. So then the edges start behaving as simply supported edges, and if the load increases, only this span moment can increase. This moment cannot increase any further. Only the span moment can keep increasing, and at one particular point, the span moment will reach such a high value that the positive yield line will form. And once this is formed, then that is the end of the slab. It cannot take any more moments, and collapse will occur. Okay, so what this is the mechanism. So you have W square by 12 and W square by 24 at the edges and at the span. Okay, and initially what will happen is you have formation of this negative yield lines, or at the edges you will start having what is known as a plastic. I mean, if it's a beam, we call it as a plastic hinge. If it's a slab, we call it as a yield line. Okay, so we start having an yield line here and a yield line here corresponding to this edge and this edge. Okay, and beyond that we cannot have any more increase in moment. finally what will happen is, so one thing you should notice, here and here yield line is formed. Okay, but even after this, you will have curved deformed shape only. You will still not have straight line deformed shape. Okay, because it is not yet collapsed. It's not yet formed a mechanism. Two yield lines are formed, but three is needed to form a mechanism. So unless the third yield line also forms, you will not have a mechanism, and your deflected shape will still be curved, smooth curve, parabola, whatever it is. Once this third yield line also forms, then you start having this mechanism type of a deflected shape. Okay, so these are things that you just notice. These are some assumptions with regard to the yield line theory. So all the steel is fully yielded at the location of the yield lines. Okay, meaning that if I draw a yield line like this, that means all the reinforcements at this particular point, the middle of all the reinforcements have yielded. Okay, I do not have a situation where about this much reinforcements have yielded at the middle, while here and all it's not yielded. I cannot take a case like that. Okay, if I draw a yield line across the yield line entirely, at that particular section, all the reinforcement has yielded. After the yield line is formed at that particular location, you will have rotation, but you will not have any increase in the bending moment. Okay, the yield line, this we've seen before. Yield line separates the slab into parts which rotate rigidly as straight lines. Yield lines, the yield lines which you draw should be straight. Okay, I cannot have a curve. I cannot have a yield curve. That's why it's called as a yield line. It can only be straight lines. I cannot have a yield line which is going like this or a curved. That and all I cannot have. Yield line should be straight. And finally, also the bending moment is same at all points along the yield line. So whatever is the bending moment here should be same throughout this place. So the bending moment here should be the same as here, as here, as here, as here. Okay, and it is constant, meaning that it is same and constant as well, meaning that if I increase the load further, the bending moment along the yield line will not increase. It will still remain the same. Only at other locations the bending moment will increase. So how to draw yield lines? Some guidelines. The paths formed after the yield line should rotate about the support or the center to center line between the two edges. If it's supported on columns, then between two columns, the two paths on the two paths on both sides of the yield line, they will rotate as rigid paths. So the yield lines will, from the positive bending moment, will start at the interior of the slab and run to the nearest support. Okay, so if you have a positive moment, so this is what is over here. Okay, so this is where the positive moment is happening. So the yield line should start somewhere over here and it should go to this support. Okay, this is the nearest support for this yield line, so it will go to this edge and this edge. Okay, that is what is mentioned over here. The yield lines that start with the negative bending moments, they will run close to and parallel to the fixed or continuous supports. So I showed you in the previous fixed slab support that you had a yield line over here. Okay, that's where the support is. So you will have them running parallel to the support. Okay, so these are all in general. In specific cases, like if you have a point load, point load will cause a bending moment at that part under the point load. So from that point, you will have yield lines which start from the point load and radiate outward. Okay, I think the next slide I have some figures. The lines of deflection of a slab are a good indication of the yield lines. Okay, so if you're able to see how a slab will deflect, you'll be able to predict. Based on that, you can actually draw the yield lines. Okay, so this basically represents your these 2 points, the second and third point. Okay, so this is some examples. One-way continuous slab. So you have a continuous support here and a continuous support negative moments. So you have a negative yield line here, another negative yield line here. Positive yield line will obviously be at the middle. So this is there. This is a one-way continuous slab, very similar to your fixed slab, except that it will occur recurrently. So you have negative yield lines next to this continuous support and positive yield lines perpendicular to the direction of the maximum moment. Okay, no negative yield lines at simple supports. Okay, This one, okay, yeah. So this is drawing number 2. So I see that this is all simply supported, all 4 sides. So therefore, you will not have any negative yield lines. And this is square as well. Okay, this is a square slab, and so therefore, if you have a point load over here, okay, this is two-way. By the way, this is not a one-way slab. This is a two-way slab, simply supported on 4 sides. Okay, so when you have this kind of a situation, you can predict where the deflection will be maximum in the slab. Where is the which point is the maximum deflection in this particular slab, or maximum moment? Where does the maximum moment occur in this slab? UDL, square slab, simply supported on all 4 sides. Where is the maximum bending moment?
The center.
At the center, exactly. It's exactly the center. Okay. So this is the point of maximum minimum moment, and so therefore all these edges are equidistant from it. And in such a case, you will have it radiating towards the corners. The yield lines just go towards the corner of the slabs, and they're all positive yield lines because all the moments are positive, because it's a simply supported slab. And the same thing if I change it to a rectangle. Okay, if I change it to a rectangle, it's very similar, except that no, it becomes. Have you seen the shape recently in today's class? Have you seen a similar shape today's class?
Yes, sir.
For what did you see it?
Like you were showing the
Load
distribution.
distribution.
Very similar shape. Okay, so you have a good amount of deflection somewhere over here, and so therefore it kind of goes to a particular distance, and from there at a 45-degree dispersion, you will have the yield lines separating out. Okay, if it's a rectangular slab, rectangular two-way slab, simply supported on all 4 sides. So these are some ways to visually just be able to predict how yield lines will look. So now some more difficult or more non-standard cases. Okay, these are not that easy to predict. In fact, it requires a bit of intuition to actually predict yield lines whenever you have these kind of cases. So this is a peculiar case where you have 2 clamped supports adjacent, and you have a column support at near one vertex. Okay, and it's of course uniformly distributed load. So here I do not know exactly where the maximum deflection might be. Somewhere over here, maybe the maximum deflection happens. Okay, maximum deflection will not be at the free edge because there's a column over here. So I do not expect the maximum deflection to be at this vertex. If this column was not there, maximum deflection would be over here. But that's not the case. So therefore, I have the maximum span moment to be occurring somewhere over here, probably, most probably. And from there, I have it deviating to this edge and that edge, and of course to the corner where I have support. So there's a support over here. So there's one radiating towards the intersection of these 2 supports. In addition, since these 2 are negative, these are fixed supports, I have negative moment there, and therefore I have negative yield lines. Now, as a sub question, I'll ask you something else. Imagine that this column was not there. What changes would be there to this yield line diagram if this column was not there? What changes do you think will be there to this yield line diagram?
The point of intersection will be like much closer towards the column.
Much closer to the point. Okay, fine. Let's see. Any other answers? Any other predictions? So basically what you're going to have in the slab is 2 clamped edges, nothing else. No other support, no column support. The other 2 adjacent edges are free, and you have same UDL. So one of your friends says that the intersection point of those 3 positive yield lines will go closer to the vertex, to the free edge. Okay. Any other differences?
So the yield line might be a diagonal, sir. The
from
diagonal
where to where?
passing to the support ends.
Oh, directly from the support, the corner, directly from the supported corner to the unsupported corner.
So like from the point 1 and point 2 would be shifted
okay.
to the support near the support, sir.
0.1 and which one for come again?
Sir, like so there are two sides, no sir, two clamp supports, no sir.
Okay,
So
okay.
the yes sir, the point where you are pointing
Okay.
from to the other side.
Here.
Yes sir, from there to the other side.
Or like diagonally like this.
Yes sir.
Okay. Good. Yes. Good prediction. Anybody else? Anything else? Any other differences? Okay, you said there's a lead line going from this support to this support. What lead line is it? Is it positive?
Yes sir, it will be positive, sir.
Positive. Okay. Any other answer? See, basically, just imagine this is clamp support. This is a clamp support. The other two are free. What type of bending moments will you have in this slab? Will you have sagging and hogging moments? If this column was not there, obviously. Because only when you have hogging and sagging, you have positive moment and negative moment, and so therefore positive yield line and negative yield line. So, okay, I take your answer. This is good. I have a yield line going from this corner to this corner, fine. But what type of yield line is it? Is it positive or negative? What type of moments exist in that slab, first of all? Do you have positive moments in that slab? If you have only two clamp supports on adjacent edges and no other support. Think about it. Actually, you will have only hogging moments in this particular slab. If you do not have this column, entire slab only has negative moments. Okay, imagine a cantilever. You have one end fixed, other end is free. Some load you have. The only moment you have in a cantilever is a negative moment, no other moment. So you just imagine this as two cantilevers intersected at a common vertex. Okay, it's just something like that. And therefore your yield line also forms in a diagonal to that. Okay, so that answer which he gave, that the diagonal is correct. Okay, it would actually form from here to here. Only thing is it's probably not, it's not a positive yield line, it will be a negative yield line. Okay, good answer though, that you are able to predict that diagonal. Okay, but anyway, for this particular case, this column, we have seen what happens. This is a different one. I have a circular slab supported on 4 columns. Okay, and subjected to a certain load. It's only 4 columns. There is no boundary support, no clamp support, no simple support, just 4 point supports like columns. Okay, so this one is also relatively easy to predict. Okay, you will just have it. You just have to imagine how it deflects, and you will be able to predict that there will be positive yield lines going outward radially. Okay, one along this, basically like on your principal directions. Okay, this is one principal direction, this is another principal direction. Okay, so one going this way, one going this way. That's it. That's your positive yield lines. You will do not have any negative yield lines because you do not have any such supports. So these are some typical examples of using yield line theory. Okay. So like this, some simple examples I can ask. Like I can give you some random. Will not make it very complicated. Something very similar to these things. Like what I asked you. No, I showed you this and asked you what happens if this column is not there, and you were able to give some answer, which was pretty decent answer, good answer to give. So like that, some small changes I may ask. Like this is the slab. Draw its yield lines. Probably state how you decided that these are the yield lines. Something like that I can ask. For 2 marks or a small question. So yield line theory, you will not have any. I will not be asking any analysis or anything. Just conceptual questions and questions like this. Draw the yield line approximately. Use your intuition and draw an yield line for this. Okay. So like that, I can ask some questions. Okay, so I'll be stopping with this today. This flat slabs, what I'm planning to do is, because of the lack of time, my idea is that I'm going to, I'll cover some concepts about procedural concepts about this. How to design what, I mean, what kind of things are, how to calculate the moments and those things. Then I'll share to you a PDF of a certain design example. You have to go through it, read it, submit an assignment of a design problem of a flat slab. Okay. So anyway, this flat slab will be covered next week. And I think your class rep would have told you tomorrow. He asked me to shift the class tomorrow morning's class to some other date, but unfortunately, I do not have any convenient slots at all on any other day except. In fact, I do not have any other convenient slot. Wednesdays I'm booked for 3 hours. Thursday, Friday also 2 hours per day. Okay, and he offered me F slot or some other highway payment slot, and all those slots also I saw it's not. It is very continuous. It becomes very continuous for me. I have to sit at a stretch for 3 or 4 hours to take classes. I cannot do that. So tomorrow's class I'll be taking. Okay, Wednesday, Friday I will be canceling. Okay, no class on Friday. So if they declare it a holiday on Friday, then that means they'll be giving an additional day on some Saturday. That's what usually happens. So in that case, next Tuesday I'll take only 1 hour. If it is announced as a holiday on Friday, if it is not announced as a holiday on Friday, then Tuesday will be 2 hours. Coming Tuesday. Okay. Tomorrow normal 1 hour class I'll take. It's not that I do not want you to go free for. It's not that I don't want to leave you free, but you know how late we started this course, so I do not have any other way. Okay, that's the reason that I am actually not. I'm proceeding with tomorrow's class. That's the reason.